Hello, everyone, and welcome to the AI for Food Security Challenge. My name is Irene Benito, and I am the Product Marketing Manager for Government at Planet. It's really my pleasure to join all of you here today at this webinar. It's the second informative webinar on this challenge, and you'll get a chance to ask any technical questions that you may have. As you probably know, the challenge focuses on the use of cutting-edge Earth observation datasets for the development of solutions that enhance food security. We're thrilled to bring together participants from around the world, and we really want to find the best machine learning AI solution for crop identification using Planet Fusion and Sentinel-1 and Sentinel-2 data. Before I go into further details on the content of the challenge, let me remind you that it's organized by Planet, Technical University of Munich, DLR, the Radiant Earth Foundation, and of course, kindly hosted by ESA AI4EO platform. The challenge will run from the 4th of October until the 19th of December. There's really still time to send an incredible submission, so please make sure that you get to work as soon as possible. I think that many of you are here today because we all share a vision that data is the new oil. And I don't refer to oil as a dirty fossil fuel, but the main analogy here is really that data is a source of power. This cannot be more true than with Earth observation data. It's extremely valuable for understanding the Earth's resources, and this includes agricultural resources. And that's why it's such a fantastic challenge, because you'll be able to have, for the first time ever, 3 excellent data sets combined. Firstly, you're having Sentinel-1 and Sentinel-2, which, as you know, is part of the Copernicus program, and Copernicus is really the crown jewel of public Earth observation programs. Secondly, the challenge also draws from Planet Fusion data, and this is extraordinary not only because the dataset is unmatched, but because it's the first time the Fusion data has been made publicly available for a challenge. It is in fact the first time the Daily Planet data has been made available for this machine learning challenge. Let me tell you just a bit about Planet Fusion data. Planet Fusion brings together the strengths of several public datasets, of Sentinel-2, of Landsat, and of MODIS, and it combines them with Planet's unique set of PlanetScope imagery. For those of you that are not extremely familiar with Planet data, you may want to know that we have over 200 Earth observation satellites orbiting the Earth every day. And with this, we're providing near daily revisits of every point on Earth at a 3 to 5 meter resolution. This constellation, which we call DOVES, is not only the largest constellation of Earth observation satellites in the history of humankind, but it's also unique in that it provides the imagery at the highest available combination of revisit and spatial and spectral resolution. Planet Fusion leverages this source of high resolution, near daily planet imagery, and then combines it with the public sets I mentioned, with Sentinel-2, with Landsat, and with MODIS. With this, we provide a unified, stable, and richly informative dataset, a stream that is uninterrupted, cloud-free, and gap-free, that is radiometrically accurate and is consistent, and that is, of course, optimized for quantitative workflows. However, I know that these incredible datasets are going to fuel the challenge, but the real value has to come from the solutions that you develop. You have at your disposal an incredible arsenal of data with which we hope you're going to develop solutions that will play a key role in measuring global indicators, especially those relevant to Sustainable Development Goal 2, Zero Hunger. We hope that through data science, your talent and your passion, you will work towards applications that enable, for example, to monitor large-scale inventorying of crops and crop yield forecasting, to help optimize the application of irrigation and also fertilizers, as well as to monitor the transition to sustainable and regenerative agricultural practices. And to make sure that you're well prepared for this task, we have an amazing lineup of speakers today that will provide you with all the technical information that you need for this task, as well as are available to answer any questions you may have. That concludes my introduction. I really look forward to an engaging webinar. And as you can see, I provide my contact details and my email, irene@planet.com, should you want to contact me for any further questions. Good luck to everyone.
Thank you very much, Irene. Following the introduction by Planet as the organizer of this challenge, I also want to give the floor to Nicolas Longepé from the European Space Agency, who is the the initiator of the AI4EO initiative.
Okay, thank you, Anne-Catherine. Thank you, Irene. Thanks for joining this webinar on AI for Food Security Challenge. So I'm Nicolas Njepe. I'm indeed with the PhilAbex office, part of the Directorate of Earth Observation Program at ESA, Ezrin, nearby Rome. So before we dive into the content of the challenge, I'd like to introduce a little bit of the context, and then I will let our partner Planet and so on to explain a bit more about the detail of the challenge. So why do we do this? So as you may know, AI is transforming the global economy and many business models across industrial sectors, including space and Earth observations. We believe AI has a huge but still largely untapped potential for Earth observation technology and application. So we are at a kind of crossroad of opportunities. On one end, we have AI becoming one of the most transformative technology, and on the other end, we have also a growing EO capabilities, which is delivering a unique, massive, and dynamic picture of the planet. So at ESA level, we can push for different set of activities, obviously capacity and ecosystem buildings, but also research and innovation. And actually, 1 year ago, we have started this activity about AI4EO challenge. So together with a set of industrial partners in Europe, for which you can see their logo here, led by a space tech partner in Belgium, we built this AI4EO platform that can organize and host challenge, by the way. With that, we aim to accelerate the research on AI for Earth observation to provide some kind of legacy data set, and finally bridge the gap in between the different communities and have even more people looking at, looking at Earth observation and problem on Earth that really matters. And as someone once said, I mean, there will be no planet B. So I think we should all try to look at some problem that matter and apply and develop AI for goods. So I guess this challenge is very well fitted to this three aspects. So we hope you guys can come up with great and new and innovative AI architecture. You have here an excellent data set combining the best of the three sensors. We have Sentinel-1 sensing the world with the C-band electromagnetic wave. You have also Sentinel-2 with multispectral radiation information. And as it was mentioned by Irene, you have also a great data set with Planet, which provide a daily revisit globally. So on that, I wish you will all join this great challenge organized by Planet together, Tomb, DLR, and Red Earth. It's not too late to apply and to beat your competitors and be the winner. You will get access to great prize from all the partners and the sponsors. So please join. And thanks all for attending this webinar. I hope and trust you will enjoy it. Over to you, Anne-Catherine.
Thank you very much, Nicolas. So indeed, now you've all got some inspiring thoughts from Planet and from ESA on joining this challenge. But what is the challenge about? We will get an explanation from Giovanni Marchisio, from the Vice President of Analytics and a fellow at Planet, who will explain to you what the challenge is about and what the data are about.
Welcome to the AI for Food Security Challenge. My name is Giovanni Marchisio and I work for Planet. Identification of crop types when done on a large scale plays an important role in forecasting food production in areas where cadastral information is not readily available. Remote sensing makes it possible to perform large-scale crop monitoring and inventory from space. The focus of the AI for Food Security Challenge is to develop machine learning models for crop identification using measurements taken by a variety of satellite sensors. You can access the challenge from the AI4EO website. So this is the main page that shows the current challenge, along with future and past challenges. To access the current one, you click onto this blue banner, and you're presented with two tracks. One which contains the data from South Africa, and the other one data from Germany. Now, what is the difference? In the first track, you're provided with field boundaries and ground truth for 5 different crop types. These are the training data which contain hundreds of fields and are shown in green here on the left. The challenge is to develop machine learning models that can correctly identify the crops shown in red on the right. The data, again, as I said, is from South Africa and consists of winter crops grown during the 2017 season. The second track adds a new element to the challenge. The data is from Germany, but it comes from two different growing seasons. In this challenge, you are provided with the training data consisting of field boundaries and ground truth from 2018, shown here in green on the right, and you are asked to classify the fields shown in red on the left. Although the geographical region is the same, the data is from a different season, that is 2018. Also, in the second track, there are 9 different crop types. And now a few words about the data sources and what makes this challenge unique. For the first time, we are providing data that includes daily observations. These are the result of a new process that we have here at Planet. These are Planet Fusion time series, which consist of the 3-meter daily cloud-free 4-band time series harmonized with Sentinel-2. So there is beautiful data to work with, is analysis-ready data. All the pre-processing has been done for you. And the advantage of using this new data stream is that you have access to temporal phenometrics, which describe in detail the evolution of different type of crops through the growing season. Complementary to this is a time series of Sentinel-2 data. So this is not acquired daily, but it has much wider spectral coverage, consisting of 12 bands that go from the visible near-infrared into the short-wave infrared. The Planet Fusion, by contrast, has only 4 bands, which cover the visible part of the spectrum and the near-infrared. The Sentinel-2 data is a coarser resolution than the Planet data, is 10 meters. Actually, 10 meters is not the native resolution for all 12 bands, but all 12 bands are being upsampled to 10 meters to facilitate your analytics. And then the last complementary data source is Sentinel-1, which is a synthetic aperture radar data. And it is ideal for detecting textures and also moisture. And we provide vertical and horizontal orientations for those. A few more words about the Planet Fusion time series. So, as I said before, it does result from fusion with the different data sources. And on the left here, you can see the input PlanetScope top of the atmospheric reflectance scenes. In the middle is harmonized Landsat Sentinel, which is one of the data sources we use for fusion and calibration. On the result is the time series we are providing for this challenge. So the result, as I said before, is a daily gut field high resolution time series that captures beautifully the evolution of the different type of crops on a daily basis. Now, fusion is a result of calibrating our PlanetScope scenes against MODIS, removing cloud and cloud shadows, and also harmonizing against HLS, harmonized Landsat Sentinel, and Sentinel-2. Work in progress also promises to incorporate Sentinel-1. But I'll skip over this. You will have access to documentation which goes into the glory details of how the fusion process works, and there are also a number of publications in the literature. This is a graph that shows the value of using daily data versus more sparse data. On the horizontal axis is a day of the year for an entire full year. On the vertical axis, I am plotting NDVI, normalized difference vegetation index, which is one of the classical vegetation indices used in agricultural analytics. And the daily time series is represented by this combination of white and gray circles. And by contrast, you can see that Landsat and Sentinel would provide respectively the measurements shown in blue circles for Landsat and square red squares for Sentinel-2. So what I'm trying to impress here is the fact that we're looking at a crop which is harvested multiple times through the growing season. It is alfalfa, and unless you have daily measurements, you cannot actually capture the dynamic of the crops. The blue and the red measurements would probably fail to capture the characteristic temporal signature and miss some of the harvest cycles of this crop. Along this line, if you do simple clustering of the temporal signatures of the area shown on the right, you see some interesting differentiation emerging. So shown here on the left is the same type of NDVI analysis. So the NDVI is the vertical axis. The horizontal axis again is the day of the year for the full year. And what you see here plotted are the centroid of the cluster corresponding to the clustering shown on the right. And you can see that this simple step does already a beautiful job of differentiating among different crop types. You can see that there is differentiation in the NDVI curves. There is green up happening at different levels and with slightly different phase shifts. And there is an harvest event typically towards the end of the summer that varies according to the crop type. In one case, we see evidence that this is a dual harvest crop. It could be the same type of crop, or it could be a different type of crop plotted in the second part of the season. In the case of the NTVI signature of shown here in red is particularly interesting because this corresponds to wild vegetation or deciduous trees. And as a matter of fact, it has green up like some of the other vegetation types here at the beginning of the spring, but then there is no evident harvest event, and the NDVI curve subside only later in the fall. So this is typical of wild vegetation or deciduous trees. Now, this is also explained in detail in one paper that was accepted by a news or publication. And one of my colleagues will go over this later on. What I want to emphasize here is the fact that the NTVI curves vary slightly from season to season due primarily to different climatic conditions. So there are differences in shape and also slight phase shifts, which correspond to slightly different seeding times and slightly different harvest times across seasons. Again, this is a factor that will play an important role when you design your machine learning models for the track number 2, which is a bit more challenging because it forces you to develop models that are portable across seasons. Now, a few words about the Planet Fusion quality assurance layer that comes with it. You will find that there is a link from the notebook to this document that provides a wealth of information about the process we use for Planet Fusion for generating the time series, and also some guidance on how to use some of the quality assurance layers. So there are a couple I'd like to bring to your attention. One of them is a mask that shows our cloud and cloud shadow masking along with the buffer zone that we employed. And the second one is very interesting. It shows the date to the closest scene with natural observations. So this other quality assurance mask is useful because, for instance, for the scene shown here on the left, which corresponds to October the 2nd, 2018, The pixels shown in white on the right came from the very day, whereas the remaining pixels were interpolated from the most recent observations 2 days after, in the case of the red areas, and 3 days earlier in the case of the green areas. This mask is particularly useful because it gives you the option to train machine learning models in parallel on the real versus the interpolated data and compare the results. So in the end, so the message I want to convey to you is that this challenge is unique because for the first time we have very high cadence observations in addition to the classical complementary Sentinel-2 and Sentinel-1 data. We do believe that the future of vegetation monitoring and agriculture will actually be based on data streams that leverage multiple sensors and multiple data sources. And again, going back to the new Planet Fusion time series, we are in the process of doing phenology validation with a number of partners, and we are able actually to prove that our measurements do actually validate very well against in situ data. So a very exciting data set to work with. I hope you can make the most of it. As one of my colleagues will explain shortly, there are challenges. There is a lot of creativity probably involved in making the most of these high cadence data. And there are new frontiers that this type of data opens up to spatial temporal modeling and developing of new deep learning models in particular. One final comment. So the data is very bulky. The daily data does require a considerable amount of storage. But for those of you who prefer not to use the daily cadence data, we have made available also from the challenge website a lighter 5-day desampled version of the same data. So again, you have the option to work with the full daily data, or there is a lighter 5-day version you can use. Anyway, welcome to the challenge, and I'll pass it over to my next colleague who will go over the details of the Jupyter Notebook. Thank you all. Bye-bye.
Thank you very much, Giovanni, for the explanation on the data. Indeed, you've seen now what kind of data you can play with, but when you start to develop your AI model, Jupyter Notebooks come in very handy, and we have provided an example on the website. And Ridvan from TUM will explain a little bit more about the notebook itself.
Hello everyone, my name is Ridvan Saleh Kuzu and I am a postdoctoral researcher on Earth observation. And I'm one of the contributors of this notebook. Let me share my screen to show the notebook. You can find the notebook on AI4AO GitHub repository. If you look at the README first, you will see some introduction, as you can find the same introduction on the challenge website. This is just a short summary. But the main information about the notebook in the folder, as you see here, there are some files, including JSON files and the main notebook. In the JSON files, you will see two different options for South Africa and the Germany submission example. And later, you will see two different notebooks. In the first notebook, you will see how to download data from the Sentinel Hub. But in the main notebook, the main notebook is called a starter pack. You will see both download options and also the other statistical measurements about the data to explore the data. First of all, you will see the menu, including 4 different category requirements, the data overview. How can we process the data by using some fundamental machine learning principles, and the preparation of your submission, and also one explanation about how can we evaluate the submissions. The first of all, you will see how notebooks will be prepared, how the import functions and the requirements can be installed at the header. Later, you will see some requirements to download the data, Brandenburg and South Africa data. There are 3 options to download the data. The first option, you can just register to Radiant ML Hub and put your API key here and start downloading data. And other options, you can directly go to Radiant ML Hub website and look at as you see here, the data sets are already there as a zip file. You just download the data from there. Or as I mentioned at the beginning, from Sentinel Hub in the first notebook, you can use this notebook to download data. After downloading the data, you need to unzip the file under that data folder if you would like to use this notebook as a baseline. After unzipping, let me explain a very short structure of the data. The Brandenburg data and the South Africa data is more or less same in terms of the data structure, the folder structure. You will see Planet Fusion surface reflection data for the entire year. And also for the limited memory users, you can find the median filtered data of the same Planet Fusion source. On Sentinel-1 and Sentinel-2, you have relatively lower data size due to the less frequent observation and the resolution of the data, as you see. And for also for training, you will see a JSON file giving the labels, crop labels for each crop field. In the testing structure, the file names are the file structures are same except the ground truth JSON file. In this JSON, we don't reveal the crop IDs, except we just give the boundaries of each polygon, crop field polygons. And one tiny difference between South Africa and Brandenburg data is in Sentinel-1, Brandenburg Germany data includes both ascending and descending orbit observations. However, in South Africa data, we have only ascending orbit observation from Sentinel-1. This is the only difference. Plus, one thing you should keep in mind that Sentinel, the entire Brandenburg data covers the entire 365 days, but in South Africa, we have 244 daily observation for Planet Fusions. These are some minor differences between the data sets, but the main structures are the same for each. Assuming that you download the data and try to explore the data sets on these notebooks and visualize some statistics, you can first look at the Brandenburg Germany data. As you see, if we explore the data sets in the labels, I mean the polygons of the fields from the training area, you will see this kind of table structure, including field ID, shape area, shape length, crop ID, crop name, and the geometry of that field. If we look at test labels, as you see, similar format, but in the crop name, we don't reveal the crop name because it will be used for the evaluation of the submissions. But in the Brandenburg training and test data, we know that we have 9 different classes from wheat to forage crops. For visualization of some statistics regarding this Brandenburg training and testing area, as you see here, crop type, if we plot the crop types and the number of fields per crop types, as you see, meadows are the most common one, but it does not mean that meadows are the most common in terms of per hectare. Yes, this is because the per field distribution. If we look at the per hectare distribution, we see a different distribution. In this case, we have more common crop. It is wheat here, and the second common crop is corn. Also, you can see different crop field statistics by crop type here. And if you look at the entire training area, we also show by crop type field areas. But in the test area, you will see only green value because no data crop type is not available here for you. So let's look at some data types for Brandenburg. As you remember, we have 3 different data types: Planet Fusion, Sentinel-1, and Sentinel-2. For reading this data set, we provide a baseline reader. It is also compatible with PyTorch if you want to use directly for your training. In the Planet Reader, you just need to inject the directory of the training folders and the labels, and it will be ready for iteration for training, also for the visualization purposes. Let's look at some NDVI values and the true color values for planet data. As you see here, from different days, we have different NDVI values slightly changing for different crop types. And also we can do same visualization for Sentinel-1 data, but you know, Sentinel-1 data is a radar data, and direct visualization is not so meaningful for human eye. So that is why we decided to show the data with radar vegetation index. The details of the radar vegetation index you can find in this link from Sentinel Hub. There are other custom scripts for generating different views of the Sentinel-1, Sentinel-2, and also planet data. As you see in this radar vegetation index, we see a different view from the same fields, and also we can do same thing for Sentinel-2 data. But let's skip this and continue with South Africa data. As I told you, the data structures are same. So if you wanna check the train labels for South Africa, you will see around 1,700 entries, which means this amount of field we have for training in the first training folder, because as if you already explored a little bit about the data for South Africa, we have 2 different zones, the tiles. This is the first tile, and in the second tiles you will see the rest of the data for training. And here we have around 2,400 data. We have around more than 4,000 training data for South Africa. And also the same structure is valid for the test data. But here, as you see, again, the crop names are not revealed. The difference between the Brandenburg and the South Africa data, while we have 9 different crops for Germany, here we have only 5 different crop types. You can also check the different label names and the IDs from this grant truth. If we look at the distribution in South Africa, the most common crop type is Lucerne Medix in terms of number of fields. But if we look at total hectare per crop type, we can see also different distributions. Again, if we look at the different tiles, training tiles for South Africa side by side, you see here the distribution of the crop types over the fields on the test area, and this is the training area, and also this is the test area. Again, no labels included for the evaluation purposes. Again, we explore Planet and Sentinel-1, Sentinel-2 for South Africa. You see this same structure for visualization here. I just skip quickly. This is Sentinel-1. And again, another visualization for the same field. This is Sentinel-2. As you see, Sentinel-2 resolution is a little bit worse compared to the Planet due to resolution differences. Okay, this is also a very important part, data processing and machine learning. First of all, you need one reader for training the data and some baseline models. We provide these baseline models, but you don't need to rely on this, and you just build your own for exceeding this baseline performances, because we didn't consider any performance optimization. We just provide some example here without extra optimization. As I mentioned at the beginning, we have different readers. You can see these readers in the utility function, utility folder of this. Here we have some utility functions. In this utility functions, you can find reader options. So Planet Reader, Sentinel-1 Reader, Sentinel-2 Reader all have the same structure. You just need to change the directory for each. And after this reader, you just need to put this reader as a parameter to data loader. So this data loader is sufficient to start your training. After some initialization of your model, we provide a baseline model based on the Denethor paper, as Giovanni mentioned at the beginning. You can rely on that paper for the details of the spatio-temporal model, because this data is entire year data and temporal data. After some optimization and determining the loss criterion, you just need to set some output parameter here. And after determining output parameter, either you just need load the already trained model, you can resume it, or you start training from scratch if you don't have any base model for these data sets. As you see, this is just a couple of iterations, but it is working with converging to optimal, but we didn't continue with the entire training here. So you can do the same with Sentinel-1 data. You don't need to change anything. You just need to change the transformer, the reader to Sentinel-1, and the rest is same. And you see again the training works. And for Sentinel-2, again, you just change the reader and keep the same structure for the rest of the model. It will work and keep training as you see here. After training your model, you have to prepare a submission. For the submission, as I mentioned at the beginning, we need a JSON files, as you see in the notebook folder, submission example JSON. So for creating this JSON, you can use this submission example for South Africa and Brandenburg. In the submission file, we have 4 different fields: field ID, crop name, crop probabilities. What we are using for the evaluation, we are using field ID and the crop ID. Crop names and crop probability are not used currently for the evaluation, but if there is a very close results, or there is a exact same performance, we can use this for determining the ranking again. But so far, crop ID and field ID what we are using. But you need to submit, you need to fill all this field for the healthy, for having the healthy evaluation at the end. And let's assume that your training is done. You read the data by using a reader, one of the readers, and you determine the output file name as a JSON, a submission JSON file. So you need to rerun your evaluation model after resuming it. And just in case, you can sort label IDs and names to be on the safe side. And later you need to fill a list of dictionary with the predictions, your model. For example, for Africa, your African model generate logits, and you create some probabilities, and field ID, crop name, and these probabilities should be filled into these lists. So later you just need to write this JSON file into the output file location. And if you wanna check if this file submission file is valid or not, also you can look at, this is a check for the validation. if it is in the expected format. And also you can visualize the format, the submission format here, as you see, the main column. This is the same actually for Brandenburg submission example. The only difference, you need a different model for Brandenburg, different input files for Brandenburg. So let me clarify also evaluation of submission. There were many questions from the previous panel about the evaluation metrics. Actually, our evaluation metrics is something customized for this challenge. It is inspired from categorical cross entropy loss. But if you are familiar with this loss, it is mostly based on using probability estimation. Y hat should be probabilities, and Y is the original target values. But in our case, we, as Y hat, we are using the binary decision of your prediction. For example, if we look at here, these are the crop probabilities. Originally, you can expect this should be used for the cross entropy loss. You are right, but in our customized metric for this challenge, we are using this crop ID as a one-hot encoding, and the remaining probabilities is equal to 0, and only the crop ID 1, in this case this one, is corresponding to 1, and the binary one-hot encoding is used for this challenge. Also, just in case, we put an example, how can we evaluate your score is given here as a Python code. You can also check if there is an error in your expected output, and what we show you in the evaluation platform, you can check here. So that is all on my side. If you have further questions, you can also get in touch with us by using this notebook issue. Let me, yeah, in this notebook, you can create some issues if you wanna ask something, or at the end of this panel, we can discuss your questions. Yeah, thank you.
Thank you very much, Ridvan, for the explanation of the notebook. Indeed, a very good resource for everyone to run the challenge. I believe we're running a little bit late, so I suggest that we give a brief overview of the prizes that you can win when you submit your best model, because both Planet, Radiant Earth, ToomDLR, and some other sponsors have given some really exciting prizes. Which you can find on the website. Just as a reminder, for each of the tracks, the winner will get 30,000 points, the second place will get 15,000 points, and the third place will get 5,000 points, which you can then use to choose from the catalog the prize or prizes that suit you the best. And so we have prizes from our organizers here. Perhaps Giovanni, you can briefly introduce the prizes from Planet.
Yes, so we offer a selection of prizes ranging for the top prize, which is a 3-month paid internship with Planet. And it would be either with the office in Berlin or the headquarters in San Francisco, based on the preference and geography of the winner. It's a great opportunity for one of you to become embedded in one of our most advanced analytic engineering teams at Planet. We are working on a number of problems which are of global interest, which have a wide-ranging effect in terms of addressing measurements related to the global sustainable goals of the United Nations. So a very exciting environment to be, exciting also from the point of view not just of the people you're working with, but the abundance of data that we have available on a global scale. Alternatives, we also offer vouchers for Planet Fusion monitoring. So this is 12 vouchers valued at 5,000 points each, and through these, you will have access to daily time series covering an entire year. The location will be totally of your choice. The size of each of the data sets will be about 625 square kilometers in size. And as I said, full flexibility. We have data available from all over the world. We cover the landmass of the planet every day. And so we can reproduce the data for you going back to January 2018. So that's actually our offering. And I'll pass it over to our colleague at Radiant.
Hi, thanks everyone. Can you hear me?
Oh, yes. Hi, Amber.
Great. Hi. So as most of you know, Radiant Earth is a nonprofit which has created and maintains Radiant ML Hub, an open library for high quality benchmark training data and soon a model repository. Radiant ML Hub is actually hosting the data sets for this challenge. And so we are coming in to offer 2 paid summer internships, which will run from June to August in 2022. The internship is fully remote and it will be working with our team, which is based across the United States and Nigeria. And each of these internships is worth 10,000 AI for EO points. There's no defined focus here, so there's a lot of flexibility for the winner to frame their interest relevant to the work that we are doing. And there's only one eligibility requirement, which is that the winner should not be residing in a country under sanction by the US government. But we're very excited about the challenge and happy to provide these 2 internships to the lucky winners.
Thank you, Amber.
Sure.
And then as well, TUM DLR is offering a research day. Ridvan, can you maybe tell us a little bit more about it?
Hello. At TUM DLR, we have offering some internship position to the contributors of this challenge if they win the prize, and also we have 3 to 6 months research with the AI4 Future Lab projects, and we provide some financial support and travel accommodations to the winners. For the details, you can also look at the definition of the challenge, and you can freely get in touch with us to get more detailed information. Thank you.
Thank you, Ridvan. So indeed, some very exciting prizes from the organizers. You can also get subscriptions to cloud platforms, Microsoft Azure credits, mentoring from several of our partners, as well as subscriptions to Sentinel Hub. So I hope this all engages you to give your best model, or to provide your best model for this, for both of the German and the South African challenge. But I see in the meanwhile, we've received quite a few questions. So we'll start with the first question. Is the starter model fed the entire image box of a parcel, or is it a cropped polygon? Also, does the input shape matter for that model?
Let me shortly explain. We don't use the entire bounding box for the training. It is a cropped parcel, a cropped polygon, and the shape actually matter for this model. Actually, if you look at the transformation functions in the detailed utility functions, we keep this resizing to have the same input size for each polygon. So yeah, you need to resize to use this model as it is. But if you want to build your custom model, yeah, of course you can make something free of this limitation in your approach.
Okay. Another question came from Kamal, and he wonders, from your past experience with machine learning, deep learning models so far, how successful are models built on interpolated satellite imagery? Whether the interpolation was due to cloud masks or missing data, wouldn't this offset the ground truth state too much?
I can try to answer that. So this is a new product, and we just started experimenting with it. And the experiments we're doing are in the realm of agriculture and change detection. So when it comes to agriculture, we found that the effect of the interpolation doesn't seem to alter the results of the machine learning models. When it comes to change detection, especially in areas where there is extended interpolation due to cloud and the snow, especially in the winter months and in northern latitudes, yes, there are problems. To that effect, as I explained during my presentation, we are providing a quality assurance mask that shows how much of the data was interpolated and what was the time gap. So my recommendation is, if you're really concerned about this, you can do the following. You can train 2 machine learning models in parallel, one on the full daily interpolated time series, and the other one actually, you can actually use the mask to your advantage to only use the real data and not the interpolated data for your training, and then compare the results and make a decision.
Okay, great, thank you. And then we have 2 questions that are, I think, a little bit linked. One question on the time it takes to download the data sets, because apparently it takes a long time to download the data sets, and the question is there a way around that?
Let me answer this. Actually, I cannot say any time, but the data size is more than 250 gigabyte in total, maybe close to 300 giga. As I mentioned at the beginning of the notebook presentation, you have 3 options. One is using the notebook. If you couldn't manage it with the notebook, you can directly look at the Radiant Earth website and download the data as a zip file. Or you can also have another option. In the main notebook, we provide the codes, the library, Radiant Machine Learning library for downloading the data, but the additional notebook, you can see also the data downloading with Sentinel Hub Python libraries. You can try any of them and find the best way for you, but totally it is around 300 giga.
And I believe with the Sentinel Hub, you can clip the data, right, before downloading?
I don't know. I don't want
Yes,
to give
that's true. That's true. You can clip the data to the field boundaries. It also may answer partially the first question. So if you download through Radiant Earth, you will be downloading data in bulk. If you actually use a Sentinel Hub, you can clip the data to the field boundaries, which gives you an option to not to use all the labeled data. You can just use a subset of the labeled data, if that is concerned. Another tip I would like to give, which I tried to give in my presentation, is that there is a downsized temporal version of the Planet Fusion dataset is only every 5 days. So by you downloading that portion of the data, you will be reducing the data size by a factor of 5. So yeah, you don't have to work the full daily time series. If your computational resources are modest, I encourage you to use the sample data set that would speed up your download by a factor of 5.
And I believe that the question perhaps that already answers the next question. A team is using Google Colab for modeling, but because of memory limitations, which data set would you recommend?
Well, again, if you have memory limitation, I would recommend using the 5-day sample version. On the other hand, it also depends upon what model you're using again. So if you're using LSTM over a long time memory span, then it doesn't really make, well, okay, again, I would go for the sample version, but it's up actually, it's also a dependency of the model you're using, really, so.
We also had some questions in the chat, which were answered in the chat, but I just want to put them here as well. There was a question about the 3 types of data, Planet Fusion, Sentinel-1 and Sentinel-2. So the same model will predict for each of the data sets, or can we use different models for each of the data?
Yeah, I try to answer that. So you have full flexibility in your modeling approach. Definitely, you can use separate models for each of the data sources and then integrate them at the end when it comes to making a decision on the crop type, or you can develop a model that works on all three sources of data. So I want to remind you all that 75% of the score will be based on the quantitative evaluation, but 25 will be based on a qualitative evaluation, and the judges will look to what extent you made use of all three data sources in arriving to the final solution. So with that respect, regardless of use of separate models for each data source or one model for all three, make sure you make use of all three and you integrate your analytics.
Okay, and are participants allowed to publish research papers based on this challenge?
Yes, of course, and eventually it's up to the publisher, of course, to accept or reject papers, but the data set would be open source at the end of the challenge for the benefit of the Earth observation and machine learning community, and I hope it will be a source of interesting publications in the years to come.
And regarding the different data sets, so the Sentinel-1 and Sentinel-2 data, are they taken at the same time? And do we know to which day of the planet data these correspond?
Okay, can my friends at the Technical University of Munich answer that? Actually, that was processed by Synergize. Well, the planet data is taken every day. So if you have timestamps for Sentinel-1, Sentinel-2, you can definitely correlate to the same date.
Yeah. And normally, because of the acquisition schedules of Sentinel-1 and Sentinel-2, they won't always be taken on the exact same day. But the timestamps should also be available in the data sets for Sentinel-1 and Sentinel-2.
Yeah, typically be every 5 days for Sentinel-1, Sentinel-2, and yeah, you can easily find out the matching time frame in the planet data.
Are there any other questions at this moment? If not, I think we have just finished our hour-long webinar. And then I want to thank you very much, Giovanni and Ridwan, Amber, and Irene and Nicola for speaking, for answering the questions, all of the participants as well for joining the webinar. And I hope you're already in the challenge or going to start participating in the challenge. If there's any further questions, don't hesitate to use the GitHub, use the forum on the AI4EO platform, or email us at support@ai4eo.eu. We're happy to help you out. Thank you all very much and have a nice evening or rest of the day.